Right, okay, welcome to my talk. My name is Ray. Today I'm going to talk to you about a family of efficient nonlinear protocols in privacy-preserving machine learning. This is a joint work with Lijing and Ziyu, who are my colleagues from Huawei, and also Hongrui and Professor Yu from Shanghai Jiao University. To start with, privacy-preserving machine learning is a useful but expensive approach to machine learning that aims to protect individual privacy while allowing effective training and inference of machine learning models. We are currently focusing on the MPC-based PML and how we can make it more efficient in practice. Here are some relevant applications. The first question is, why are we interested in nonlinear functions? Recall that our aim is to improve the performance of privacy-preserving machine learning, and through experiment we found that the time spent on nonlinear operations during training or inference constitutes a significant portion of the total time. This figure shows the percentage of time that value function takes up in the total inference on different models. And as we can see from this figure, on average it accounts for like 80% of total inference time, which is really a lot. Therefore, we believe that improving the performance of nonlinear operations can greatly enhance the performance of the end-to-end training and inference. The rest of this talk will focus on protocol designs as follows. First, I will introduce the basis of all nonlinear function protocols presented in our paper, which is a new way of determining the sign of input. Then I will provide a detailed explanation of how to use our core protocol, which is a derailing protocol based on the sign destination principle. Once we have that, we can use it as building block to construct all other nonlinear function protocols. And finally, I will quickly evaluate the performance of our protocols. Before introducing our sign destination principle, we first need to define the field terms. And due to the time constraints, we will only discuss the definition for positive inputs here, and the examples we used are also for positive numbers. If you would like to know the complete version, please refer to our paper. For the first definition, we define the effective bit length of an input x as lambda, and the way we count lambda is by finding the position of the first non-zero bit of its absolute value. Let's look at a simple example. For an 8-bit input x, the first thing we do is we find its absolute value, and since it's positive, it's just itself. And then what we do is we find the position of the first non-zero bit, and as we can see, counting from the right, it's the 7th bit. So the effective bit length of x is just 7. The second definition is for truncation, and we define the truncation of a positive input x to k bits, denoted as trcxk, as removing the last k bits of x and padding k zeros in front of it. Again, let's look at an example. Here we have an 8-bit input x, and we want to calculate the truncation of x to 4 bits. So we first remove the last 4 bits of x, then we put 4 zeros in front of it, and here is our result. Okay, now with these two definitions, we are ready to introduce our key sign destination principle. To determine the sign of input, the commonly used method is to extract the most significant bit of the input. However, we determine the sign of the input based on the output of a target truncation, which is the truncation of x to lambda minus 1 bit. And our target values are 1 and q minus 1, where the output of 1 indicates a positive input, and the output of q minus 1 indicates a negative input. For example, for an input x, the lambda is 7 as calculated before, and the output of our target truncation, which is the truncation of x to 11 minus 1 bit, which is 7 minus 1, which is 6, is just 1. And therefore, x is positive. Similarly, for an input y, its lambda is 6, and the output of the target truncation is q minus 1, which means y is negative. Now we have this sign destination principle, and we can start building a practical three-party DRAM protocol. And our main challenge is how to securely obtain the target value in a private computing setting. Let's first take a high-level overview of the general process of our DRAM protocol. At the beginning, P0 and P1 as two computing parties both hold 2 out of 2 secret shares of the input. And in step 1, they locally perform repeated truncations on their secret shares and obtain a set of results in an array, denoted as UI. Then P0 and P1 perform some linear operations on UI to obtain WI and send it to P2. P2 reconstructs the shares and searches for the target value within WI, and by determining the sign of the inputs based on the target value, P2 sends the results back to P0 and P1. And finally, P0 and P1 can proceed with further computations or directly return the results. Now you may have questions about why repeated truncations are performed in step 1, what specifically the operations are involved in step 2, and why these choices were made. In the following slides, we will gradually delve into each step and explain the motivations behind our design. So, firstly, the necessity of repeated truncations. Remember, our aim is to retrieve the output of the target truncation, which is the truncation of x to lambda minus 1 bit, in order to determine the sign. Our first challenge is that in a private computing setting, the input is kept confidential, which means that we have no access to the lambda. Fortunately, the position of the input Lx is usually public. So what we can do is we can perform Lx plus 1 truncations, starting from truncating 0 bit and increasing by 1 bit each time. So basically what we're doing is we iterate through all possible truncations to ensure that our target truncation, which is highlighted in pink, is included in the results array. And by doing this, it seems like we have addressed our first challenge. However, this approach raises some security concerns because in a private computing setting, we want to ensure that no information about the input is leaked throughout the protocol. And when the assisting party P2 reconstructs the entire array, P2 can see the inputs at the first element in the array, and this is not what we want. Our solution to this involves some simple linear operations. We first subtract 1 from each term in the array to transfer our target value from 1 to 0, and then we multiply each term by a random number for masking. By doing this, we can ensure that our target value remains distinguishable after masking, and while all other elements are masked to prevent information leakage. And as we can see from on the right-hand side, our target value is now transferred to 0, and all other elements are just random numbers. After that, a random permutation is performed to prevent P2 from getting the effective bit of input by observing the location where the target value appears. And we call this process shuffling. There is one last thing we need to consider. In practical situations, each truncation can cause a 1-bit error with a 50% chance. So we will now discuss how the truncation errors affect our DRAM protocol. Here's an array of outcomes for repeated truncations without error, and on the right-hand side is the array with error. Now we can see there is a possibility of having consecutive ones before counting zeros. After applying the aforementioned linear operations, these consecutive ones will be transferred into multiple scattered zeros in the array. And what P2 could do is P2 can determine the upper bounds of the input size by counting the number of zeros in the array. For example, after reconstruction, if there are 3 zeros in the array, this means that the input is smaller than 2 to the power of Lx minus 2. However, even being able to narrow the range of the input size is not allowed in a private computing setting. Our solution to this is to perform a recursive summation as shown. And as you can see, for the first element in the new array, we add from the truncation of x to 0 bit to the truncation of x to 8 bits. And for the second element in the new array, we add from the truncation of x to 1 bit to the truncation of x to 8 bits, and etc. And by doing this, we can make sure that only one target value exists in the array. And with this, we have finally completed the construction of our three-party D-ReLU protocol. This is exactly the same algorithm as we presented in our paper. The highlighted section in step 2 and step 9 are used in the case where you don't want speech to know the outcome of the D-ReLU protocol. And what it does is it blinds the inputs using a random bit T. The highlighted sections in green in step 3 and step 4 are added specifically for the special input 0. You can find the repeated truncations in step 3, the recursive summation in step 4, and shuffling in step 5. And I hope this talk can better help you understand our core algorithm and the principles behind it. Just to summarize, we introduce a new sign destination principle, and we construct a three-party D-ReLU protocol based on it, which achieved one order of magnitude improvement compared with the state-of-art work at bits. We then use the D-ReLU protocol as a building block to build the whole family of nonlinear function protocols. All our protocols only requires 2 rounds of communication and does not require any preprocessing. With this, I conclude my talk today, and I'm happy to take any questions.
So, any questions?
Yes. Hello, can you hear me, Qingrui?
Yes.
Okay, I had a quick question. So, could you elaborate a bit more why the target value for the truncation-based sign determination was 1 and q minus 1 instead of the basic 0-1 binary test?
Yeah, sure. Well, I'll quickly pop into this page. So can you see my screen now?
Yes.
Basically, what we're doing is we're trying to find the most significant non-zero bits of the input's absolute value. So the commonly used way is to extract the MSB, which is the just the first bit on the left. However, for positive input, the most significant bit is the first non-zero bit, which, as explained before, is the 7th bit. And for the definition for a negative input is like it's a bit complicated. You can refer to our paper, but basically what we find is that for all inputs, it satisfies a pattern that when we apply the target truncation, which is the truncation of x to lambda minus 1 bit, the results of 1 indicates a positive input, and the results of q minus 1 indicates a negative input.
Yeah, thank you. Let's thank the speaker again. So this concludes our session, and thank you everyone for joining us.
Thank you.